I could be misspeaking. So we'll definitely record for him and those that are not with us. Okay, so different packets for this unit, Zach and Abby. The goldenrod packet will be the unit assignment. So even though I have questions here, this is our unit assignment, and not wide and deep, but new. Probably will assess maybe next Thursday-ish. We'll see. So the focus of our unit, which this is a similar screen that we saw yesterday, is if given a process. So it could be a chemical reaction. It could just be a description of what's going on. Can we, with confidence and justification, predict if it's spontaneous or not? And that will make more and more sense as we learn our content. So today, our focus would be entropy. And I think I will go back. Nope. Hold on a second. Nope. Sorry. All right. That is page 2. So I'm going to switch out and go to, I forget when we're on Zoom, which way to go and that kind of thing. Okay, so on page 2. So we left off yesterday explaining what do we mean by spontaneous. And if you get it, so I do have, I don't know, a definition or explanation, but it's a process that occurs without you doing anything. So for example, your clothes that you pull out of the dryer, they will just remain in a bundle unless you exert energy or you do the folding. Well, they're just going to remain in the bin until you put them in. Or we know dust will accumulate unless we do the cleaning. So all of the just normal quote unquote processes that surround us. All right. Well, how do we judge if a process is spontaneous or not? Now, remember I said that some terminology is being updated. Every chemist knows what spontaneous means, but some recent authors have been using spontaneity and thermodynamically favored interchangeably. So I will be using that terminology as well, because that may be definitely what the College Board will ask of us. So we can use the term spontaneous, but probably the College Board and more updated editions of textbooks will use the terminology of thermodynamically favored. They mean the same thing. So if it's not spontaneous or non-spontaneous, it is not thermodynamically favored. So how do we know? Three variables. So we have learned and been exposed to capital H. And as far as enthalpy is concerned, Zach, I know you know this. Are exothermic or endothermic processes more thermodynamically favored? It is. And so we could think, okay, reaction diagram, we know we're going to end up at a lower enthalpy than we start. And the sign on change in, which will be, okay, where do we end up versus where do we start? The sign, Zach, is, yeah. So usually that, but that's not an always. So it's a usually exothermic processes are thermodynamically favored. Well, there's another term, and that's our focus of today, capital S. And Adam was all about it a couple minutes ago. But the final decider that we will get on Monday is G. So these are the three thermodynamic terms. We got refreshed on what enthalpy involves and so on yesterday, had a whole chapter on it. So now we're seeing the interplay of these, but that is the final decider. So if we want to say like that's the Supreme Court, so we could like take things to the magistrate then it accelerates to maybe, I don't know, district court, so on and so on. We go to state level, and then the final decision maker, okay, is Gibbs. All right, so today, what is S? Well, S is entropy. Entropy, E is taken with energy. We use a capital S, a capital S. When I was first studying chemistry, we use two terms to represent entropy that aren't so popular today. We just said entropy is disorder or chaos. Not so much today. Today, we describe entropy as dispersion or positional probability. And I'll give many examples to clarify what we mean. Okay. At the end of the day, what we need to be able to do, if you're given a process, can we say if the process is increasing or decreasing entropy? Where if it's a positive change, that means we're increasing dispersion or positional probability. And if we are decreasing, it's negative. We are decreasing dispersion or decreasing positional probability. All right, so kind of back to, okay. So entropy, the dispersal of matter or energy. So for example, if we have a particular diagram that is showing us the solid state, and then I would say that's good gaseous state. Well, we would say this is more dispersed than that. All right, but I think more this gets us, I think, a little bit better as far as dispersion or positional probability. So our old high school, the auditorium, did it sit 800, 1200? I'm not sure. Let's say 1200 seats. So if Amanda went into the auditorium at our last high school, she could sit in the first seat, first row, or second seat, first row, or third seat, first row. So she would have 1200 options if it says 1200. Let's say that Amanda invites Porter to join her. Well, of course, Porter's going to sit next to beautiful Amanda. So Amanda will go there, Porter will go there. But maybe Amanda's like, Porter, you put on the cologne a little heavy, dude. Can you please sit there? So if she's there, we know Porter could be here or could be there. And those are both different arrangements. Yeah. Well, then maybe Amanda thinks, well, Porter, I should have invited Luke. So Amanda, Luke, Porter, but then Luke says, oh, I want to sit on that, and so on and so on. So we know probability-wise, statistic-wise, how many different arrangements. So the greater the number of people or moles of particles, the greater the different numbers of arrangements. But then they do the same thing in our new auditorium, which, I don't know, 1800? No clue how many, but definitely more seats. So if we want to think about this kind of like auditorium kind of scenario, okay, we increase entropy, one, when we have a different phase. There's a greater dispersion, yeah? So a gas possesses, of the three common states of matter, the greatest entropy, the greatest amount of dispersion. They found out it's Adam's birthday too. Okay. but also as we increase temperature. So what kind of, increases entropy? Well, when we go from solid to liquid to gas, or if we increase temperature. So if we're increasing temperature, we know temperature is directly related to kinetic energy. And if we're giving more energy of movement, that may lead to a greater number of arrangement kind of positions. All right, but also, let's see. Solid to liquid, here is an increase in volume. So again, what if we had a gas already very high dispersion, but then we allowed that gas to take on a larger volume? Well, then that would be like the 3 students going from the old high school to the new high school auditorium. Same number, but then a greater volume, which will allow for a greater number of possible arrangements. Yes. Keep going.
Like with larger elements, would they have a higher entropy because they have more electrons that are more spread out?
Yeah. Yep. Yeah. But also, if, let's just say we're not controlling volume, but we keep adding more moles, more individuals. So if Luke then would invite Sarah, and then Porter invites Abby, and so on and so on, we can just imagine the different number of possibilities in the seats in the auditorium. Okay. The handy dandy pink little sheet. Okay. So, all right. So we will find numerical values for entropy. And the greater the numerical value, of course, the greater the dispersion, the greater the positional probability. But we're often just asked for the sign. So the direction of entropy change will be positive or negative. And remember that floating 0 means standard state. Okay. Entropy increases when matter is dispersed. So there's that more modern term. Instead of saying when matter is made more chaotic, made more random. Okay, so when we're doing a phase change of solid to liquid, liquid to gas, but also if we're increasing the number of particles or an increase in volume for a gas. So just to go over, like, what are all the ways that we can increase? If we're changing phase, if we're adding or taking away particles, and then if we're increasing volume, but remember that would only play a role in the gaseous state. But we can also increase entropy by increasing temperature. Okay, so let's just apply. First, sign on enthalpy. So could we all go ahead and do that first? Are we positive or negative? And wait, so at the normal melt, what does that mean? When we see the term normal, amazing chemists, what does the term normal mean to us? Actually, just 1 atm. Whenever it's normal, it's just talking about the reference pressure. So it would be standard pressure, standard condition pressure. Excellent. Yep. Because then it'd be, we're melting at 25, we're freezing at 25, yeah. So it's just, no. So good. We need a reminder of that. That means 1 atmosphere. Okay, Rachel, do you mind reading downward? So first, not asking for numerical, asking for the sign. So if we melt something, is it if it's okay, can I give a common material suggestion of water? So we normally don't interact with a substance at all three phases in our everyday life, but we do H2O. Like think of oxygen. Do we ever interact with oxygen in the liquid or solid state? We can like theorize it, but water we can't, or sodium chloride. Do we ever interacted with the liquid or vape? No. So water. So think of how you would accomplish this, exo or endo. So sign, you got it. Now, freezing. Yeah. And then positive and then negative. Good. Do we need to discuss any? Okay, so now this. So can we think of, okay, what would be the sign though? What's going on with the dispersion? Yeah. Now, that doesn't mean they always go hand in hand. But because these are phase changes and we could be manipulating them with pressure, but usually we're adding or removing heat, hence this, yeah? And so we could be applying this last bullet, or of course, this kind of perspective. See, not terribly crazy hard. Okay. So going back here, entropy, when it is positive, that is thermodynamically favored. Okay, now that doesn't mean that if it's negative, then overall it's not, but if we're just looking at entropy, so why are processes that increase disorder or dispersion natural? Well, that has everything to do with the second law of thermodynamics. And the second law says the entropy of the universe is increasing. I bet we may not all have this, but you'd be familiar with it, I'm sure. So I don't know if anyone has had the privilege of pulling a little too hard on the drawer that you have your silverware in. Of course, clumsy me, of course. I've done that multiple times in a hurry, pull a little too hard. So when we're putting away clean dishes, sort all the forks and all the knives and all the, well, how likely is it when the drawer became free of its holdings, when it fell to the floor, did all of the knives line up and all of the forks, let alone even come near each other? Of course not. Of course not. Of course not. So, your mom knows, Sarah, that when she puts and dumps out the folded laundry or non-folded laundry, she knows that all your shirts aren't going to all line up and all the socks aren't going to, that it's just going to, make a point that she's trying to drive home or whatever else. Yeah. We know that our rooms will get messy naturally. So a thermodynamic chemist says, well, that's because nature favors a greater state of dispersion. Okay, so that is why we say that these processes that increase positional probability are thermodynamically favored. Okay. Third law of thermodynamics. Third law of thermodynamics, we see, I think I give it to us, on page 10. On page 10. Okay, the third law of thermodynamics says that a perfect crystal at 0 Kelvin has 0 entropy. What would a perfect crystal be? So what is a crystal? It is a species in the solid state where there's extreme organization of the particles. In fact, the organization is found in a regular repeating fashion. For example, we know that sucrose and sodium chloride naturally form cubes. And if we could, with an electron microscope, delve into a sugar cube or a salt cube, well, that cube, oh gosh, is made of smaller cubes and smaller cubes and smaller cubes and smaller cubes. And then we'd eventually get to one unit cell that has our chlorides and our sodiums or our sucrose. So a perfect crystal, nothing would be out of place. Everything, if it is meant to the ion position be in a 90-degree angle between the next ion, everything is in its place. It's okay that I share a personal story. When my husband proposed, I'm not sure when, close to that, he said, you know, the jeweler gave me a map of your ring. Like, a map of my ring? What are you talking about? He said, well, a jeweler actually like maps out where all of the unit cells meet, because a natural diamond has discrepancies within it, has impurities, has maybe the carbon atoms separated a little further than not. So if you ever take your ring to get cleaned and you're worried that someone traded out your diamond for a cheaper diamond, you can have someone look at the map that you bought. I don't know. I never knew that that kind of thing existed. But that just shows that in our world, even a covalent network crystal isn't perfect. Go ahead, sir.
Atoms bonded together at 0 Kelvin because the partial positive and negative charges. It would
Okay.
create a little bit of movement, which would be a little bit of
So yeah, how do we feel about that temperature? Okay, so well, yeah, I know. All right, so we define absolute zero as the temperature at which matter has no kinetic energy. We can recreate it in a lab. It's very hard. You have to use special lasers to actually hold atoms still. But then again, how do we use a laser to hold an atom still? Aren't we giving it energy to move? So we can just get there for moments and then we can't sustain that. Yeah. So again, like remember like the intangible sometimes nature of this. So this is a theoretical. What we're saying is, oh, but if you took my diamond and got it to 0 Kelvin, it would become closer to being more perfect in theory. Okay, just like the entropy of the universe. Well, why do I need to know about the universe? I just need to know about room 322 at this moment in time. In fact, just my like little area. And so yeah, this is like all, you know, a little bit non-tangible. Okay, but the deal is, if you turn to the back thermodynamic table in our white packets. Okay, so we alluded to this yesterday. Remember that previously, we just were looking at enthalpies of formation in unit 6. Okay, but now let's jump to the last column. Okay, notice it is not a change in, We call these absolute entropies. They're an assigned value based upon the stretch that the third law of thermodynamics asks us to make. Okay, so what we're basically saying is, okay, if I have 1 mole of aluminum solid at 0 Kelvin, it has 0 entropy. So at 298 Kelvin, which would be 25 Celsius, at 298, if it's 0, then what would we assign it to be? So it's something we make up that's backed up with some experimental data. But the whole thing is, yeah, we can't be at 0 Kelvin, so, and then the same thing, Al2, O2, okay, it's 0 Kelvin, it's 0 entropy, so we give it this assigned value. So it's an assigned value, that's why we call it an absolute, not change in. So notice, first off, these are all positive values, so Zach, you're so right. Unless we're at 0 Kelvin, there's going to be some movement, even in the solid state, giving some dispersion. Okay, and they're always positive, and there's no zeros, because we could only have 0 at 0 Kelvin. And when we have, for example, if we look under carbon's column, the graphite, diamond, look at the difference between solid and then we're going to gas. Now, of course, they're different substances, but just to compare like states. Okay, so we do have numerical values, but it's so much more rooted in, can we predict signs? So can we go to, I'm sorry that we're flipping around so much within this, but if we could take a look, please. In our green, I'm sorry, in our green. Okay, could I ask us to take a minute to entertain question 10 and then question 13, 10 and 13. Good. Need another minute. Ava, do you mind sharing what do you feel most strongly is the choice for 10? Absolutely. Do we need to talk? Do you mind continuing for 13? Excellent. Do we need to go through? All right, so amazingly strong ones. Can we do turn, please? 14 and 15. So take about a minute and then we'll share. Okay, whenever we're asked about increasing entropy, we're looking at, okay, are we making states of matter that are more dispersed? So do we start with solid and we're making liquid? Start with solid, making aqueous. Start with liquid and make gas. Okay, so what states do we have in reactant versus product? And if we're increasing the number of moles, so we may just have solid and solid, but do we have more moles of solid on product side? So 14, the choice is A, and 15, the choice is B. Do we want to talk? Okay, yes. I'm so glad. Okay, so in A, I have a total, okay, gas. So 3 moles of gas to 2. I'm so sorry. In which one? D. I have 3 moles of gas to 2 moles of gas. Here, it's 1 mole of gas to 2 moles of gas, but I start with solid. So I'm looking for where am I decreasing? Well, here, I'm making more moles of gas. So I can just, if I'm asked to choose the best. Is that okay? All right, enjoy your long weekend. Send an email if you believe that there's an error with grades. There, I can't wait for the concert. Yeah. Have a good rest of your day. Thank you for telling me about your sculpting. Yeah, that's enjoy your time. So excited. Are y'all absent? If that's what you're doing, and you're totally right. No. Nope. So early-ish next week. Yeah. It is.